Okay, in this video we continue our discussion on counting the number of label trees on n vertices. So in the last video we discussed these examples. Okay, for n equal to 3 there are 3 label trees on 3 vertices, and similarly okay, for n equal to 4 there are 16 labeled vertices on 4 vertices, and okay, we are developing idea to prove this Cayley's formula or Cayley's theorem. Okay, Cayley's theorem says that there are n to the n minus 2 label trees with n for n equal to greater than 2 vertices, and we already saw okay, this statement it holds for n equal to 4 and n equal to 3. Okay, so in order to prove this statement we are trying to establish a one-to-one correspondence between the total number of labeled trees on n vertices with the number of sequences of length n minus 2 on n elements, okay, or a Prufer sequence. And in the last video we saw that number of sequences of length n minus 2 on length n is n to the n minus 2. So if you are able to establish this correspondence, then that says the number of labeled trees on n vertices is n to the n minus 2. So we are trying to develop the proof idea for proving this statement. So here if you are given a labeled tree and if you are able to come up with a sequence of length n minus 2, and vice versa, if you are able to convert a sequence of length n minus 2 on n elements to a labeled tree on n vertices in a unique way, then that's enough to prove this statement. So in the last class we saw how to convert. In the last video lecture we saw how to convert a labeled tree on n vertices to sequences of length n minus 2 on n elements. So in the last video we discussed how to convert a labeled tree on n vertices to a Prufer sequence. Okay, so and we saw this example and we converted this particular tree to a sequence. So if we start with say n vertices, then the sequence will be of length n minus 2. So here we started with a tree of 9 vertices and we converted that tree to a sequence of length 7, the Prufer sequence. Okay, so if we are able to do this in the other direction in a unique way, then that's enough for the proof. Okay, so in this video we are going to go and show if you are given a sequence of length n minus 2 on n elements, then how to convert that sequence to a tree, a labeled tree on n vertices with labels 1 to n. Okay, so we are going to discuss a procedure for converting a Prufer sequence of length n minus 2 using symbols 1 to n to label trees on n vertices with labels from 1 to n. So what I am going to do is I am going to write down a procedure for this conversion, then we will work out the example. We will work out the same example. So here we will start with this sequence, and let's see whether we are able to come up with this tree, okay, using this sequence. So if you are able to do that, okay, then we can go and prove that statement. Okay, that we will do in the next video. Okay, so let's discuss how to convert a Prufer sequence to a labeled tree. Okay, so let the sequence S be say A1, A2 up to an minus 2. So here we are given a sequence of length n minus 2, and here assume that this AI okay, is from this set 1, 2 up to n, and let L be this set 1, 2, 3 up to n. Okay, so this is the procedure for converting a Prufer sequence to a label tree. So Okay, we are given this sequence and we are going to discuss how to convert such a sequence to a label tree on n vertices. Okay, so the first step is to find the smallest element, say x belonging to L and x does not belong to the sequence S. Okay, so first find the smallest element that belongs to this set L, and that element doesn't belong to S. Okay, then after that, once you find the smallest element, then what you do is you join this x to the first element of S. Okay, so you do something like this. You will create a vertex for x if such a vertex is not there in the tree. Okay, then you will create another vertex if there is no such vertex. Then we label that by a1, where a1 is the first element of this sequence. Then we join them by this edge. Okay, then after that what we do is we will delete a1 from S and this x from L. Okay, so we have a new, okay, we have this new sequence S which is equal to S minus a1 and new L, okay, which is equal to L minus that element x, where this x is the smallest element. Okay, and what we do is we repeat this procedure. Okay, in the next step what we do is again we will find the smallest element, okay, y element of L in the newly created, okay, newly created L. Okay, where this newly created L is obtained by deleting this x from L and y not equal to y not element of S. Okay, where this S is the newly obtained one after deleting a1 from S. Okay, then after that what you do is, okay, you will join this y to the first element of S. Okay, in this case first element is a2, so we deleted a1, so after that the first element will be a2. Okay, so what we do is we join to the first element of S, then after that we delete, okay, this y from L and a2 from S. Okay, exactly what we did here. Okay, and after that, okay, we have this new S, so S is equal to S minus a2. So after this step, S do not contain a1 and a2. Okay, and similarly our new L which is equal to L minus, okay, this y. So after this step y we do not contain x and y. Okay, so we repeat this process and okay, we repeat until two items remains in L. Okay, then after that what we do is, so we continue this until two items remain in L. Then after that we join, okay, these two remaining items in L. Okay, these two remaining items in L by edge. Okay, so this is the procedure for converting a Prufer sequence to a label tree. Okay, so let's go through an example. Okay, we are going to work out this example. So we will start with this particular sequence and let's see whether we could retrieve this tree. Okay. Okay, so in this case we are given this sequence, okay, where the sequence is 1 1 3, okay, 1 1 3 5 5 5 and 1, okay, 1 1 3 5 5 5 9. So here the sequence length is 1 2 3 4 5 6 7. Okay, sequence length is 7. Okay, so we are going to construct a labeled tree on 9 vertices using the labels 1 2 up to 9. Okay, so let's see how that can be done here. Okay, so here the first step is find the smallest element x in L which is not in S. Okay, then after that join x to the first element of S and then delete A1 from S and x from L, and we repeat this until two elements remain in L. Okay, then after that we join those two elements and that will finish the construction. Okay, so in this case is this one. So here A1 is this element, A2 is this, A4, A5, A6, A7. Okay, and let L be this set 1 2 3 8 9. Okay, so the first step is to find the smallest element x in L that is not in S. So let's consider 1. So we can see that 1 is here, right? Okay, so we move to the next element. Next smallest element is 2. Okay, 2 is not in S. So in the first step we set x is equal to 2. Okay, this step smallest element x belonging to L and x do not belong to S. Okay, then after that we join this x to the first element of S. Okay, so we can see that there is no vertex associated with 2. So we start with an empty tree here. Okay, then we build this tree using that procedure. Okay, so we create this vertex x and we create one for A1. Okay, A1 here is 1, right? Okay, so we create two vertices and we join them by an edge. Okay, then after that we delete this 2 from this L and the first element from this sequence. Okay, then after that we are left with this sequence. Okay, 1 3 5 5 5 9. Okay, and we delete this one and this one. Okay, so in the next step what we do is we will look for the smallest element in L, okay, which is not in this sequence. So 1 is here in this sequence, so we will move to the next smallest. The next smallest is 3. Okay, we can see that 3 is also in S, so we move to the next smallest. Okay, so next smallest is 4. So in that step our x is equal to 4. Okay, so what we do is, okay, we will join these two vertices 4 and 1. Okay, in the tree we do not have a vertex for 4. Okay, so we will create a new vertex 4, and okay, there is already one vertex for this element, right? Okay, 1 is there. So what we do is, okay, we will connect these two by this edge. Okay, then after that what we do is we will delete this x 4 from L and the current first element from this sequence yes. Okay, so that corresponds to this thing. We are removing this one. Okay, so in the next step again we will do the same thing. So we can see that okay, here L contains more than 2 elements, right? Okay, so we will look here. this, okay, we look at the smallest element in L. So here the smallest element is 1. Okay, here the smallest element, okay, is 1. So we can see that 1 is not in this sequence. Okay, so what we do is we consider this one. So in the next step our x is equal to 1. Okay, so what we do is we will add an edge from 1 to 3 in our 1 to 3 in our tree. Okay, so we can see that there is already one vertex for already a vertex for 1. So for 3 there is no such vertex. So what we do is we will create a new vertex and we label that with 3. Okay, and we will introduce this edge from 1 to 3. Okay, then after that we will delete this 1 and this 3. Okay, so our new sequence will be like s equal to 5 5 5 9. Okay, so we consider these 3 elements in the sequence. Okay, so in the next step we will look for the smallest element here, that is not in the smallest element in L is 3. Okay, 3 is not in S, so our new x is equal to 3. Okay, so what we do is we will add an edge between 3 and 5. Okay, 3 is already in the tree. Okay, so 5 is not in the tree, so we create a new vertex for 5. Okay, and we add this edge and that vertex will be labeled by 5. Then after that we will delete this from L and this from S. Okay, so after that step L contains 5 6 7 8 and 9 and S contains these 3 elements 5 5 and 9. Okay, so in the next step the smallest element is 5, but 5 is in this S, so we won't consider 5. Okay, so let's consider 6. Okay, 6 is not here, so in the next step x is equal to 6. Okay, so 6 is not in the in this tree, so we create a new vertex and we label that by 6. Okay, and we add an edge between 6 and the first element in the sequence. So first element is 5, so we add this edge. Okay, then after that we delete this 6, okay, current x and the first element of this sequence. Okay, so again we look for the smallest element in L, that is not in S. Okay, 5 is the smallest, but 5 is here. Okay, and the next smallest element is 7. So in the next step we set x is equal to 7. Okay, and we introduce an edge between 7 and 5. Okay, 5 is already there. Okay, so for 5, okay, we create, okay, for 7 we create a new vertex and we label that by 7 and we introduce this edge between this 7 and 5. Okay, then after that we delete 7 from L and 5 from this sequence S. Okay, and now we look for the smallest element here. The smallest element is 5 and 5 do not appear in this S. Okay, so that says we need to add an edge between 5 and 9. 5 is already in the tree. Okay, 9 is not there in the tree. Okay, so we add a new vertex here, 9, and we add this edge from 5 to 9. Okay, so in that case our x is equal to 5. Okay, then after that we delete this x and 9. Okay, so now we are left with 2 elements in L. Okay, so what we do is, okay, we will create, 9 is already there. Okay, 8 is not in the tree, so we will create a new vertex. We label that 8 and we introduce this edge. Okay, now we have this tree and it contains 1 2 3 4 5 6 7 8 9. Okay, all the vertices. Okay, 9 vertices. Okay, and let's see whether this looks similar to the tree that we started with. Okay, so I think I will redraw that particular tree. Okay, the tree, this particular one. Okay, let's see whether it looks something like that or not. Okay, so okay, so that case 1 is somewhere here, then 2 and 3. Okay, 1 2 4. Okay, so I think 4 were here. The 1 4 2. Okay, 1 4 2. So 1 4 2, and here we have 3. Okay, from 3 okay to 5. Okay, 5, from 5 we have 6 and 9. Okay, 5 6 and 9, something like this. 6 9, from 9 we have 8. Okay, and from 5 we have this 7. Okay, so 1 2 3 4 5 6 7 8 9. Okay, let's see whether it looks something like this tree. Okay, 1 2. Okay, it's certainly something like that. Okay, so we are able to retrieve our tree from this sequence. So it seems like, okay, we can find a one-to-one correspondence between the label tree and sequences here. Okay, so anyway, that's the proof idea, and we worked out these two examples how to convert a label tree to a sequence and back. We are given a sequence, how to convert that sequence back to that particular tree. Okay, so we will prove this statement in the next video. So the proof will be exactly similar to this procedure. So converting a label tree to a sequence and sequence to the label tree, and arguing about, okay, this is a one-to-one correspondence. Okay, so we will prove that in the next video.